Hi and welcome to this maths tutorial. Yes, we're going to do a tutorial. Now the reason we're doing a tutorial is because it's different to a class. This is a recap of what was handled in the class for those that thought I may have gone a little quick. So this is sort of something that you would skip if you understood the class 2 really well. If you didn't understand class 2 really well, this will hopefully make it a lot simpler for you and it'll make a lot more sense as to what's going on. So I'm going to be explaining stuff mainly here, and this will all hopefully pick up on what, but a bit more informal, I guess, than what we did before. And I'm certainly going to try and speak slower so that I can help you guys out if you feel like things are a bit quick before. Now, what I wanted to do was show you this first picture, which is the graph of two vectors. I'm going to just discuss a couple of points about this that'll pick up. First one I want to discuss is that if I have a vector anywhere in 3 space, like here, that vector has a magnitude, that's its length, and it has a direction that it's going in. But I can move it anywhere I want. So point number 1 is I can move a vector, and I don't affect the vector. It's like the sun coming in the window. You don't think of there just being one vector of the sun coming in the window. You think of there being a vector of the sun coming through the window, but it's coming through the window at any kind of particular position. It just happens to be orientated in a certain direction and have a certain magnitude. The second thing, and this is the thing that I think a couple of people didn't get my somewhat perhaps my reference in the class, so I'll try and explain it. What I was trying to say with the old idea of coordinate space is that when I have these vectors, I build a stage around them. And so here's a stage I built with an x-axis, a y-axis, and a z-axis. Now, why did I bother doing the thing about going between an x, y, and z space and the polar coordinates? Like, why bother showing that? What I was trying to emphasize dramatically is that while we build up this, space that we're working in as an x, y, and z space, we oftentimes change the coordinate space. We move from one coordinate space to another because that allows us to do really important things. And I was using that polar example as like a really dramatic case of that. So let's say I want to deal with these two vectors right now. The first thing I'd want to do with these vectors is swing around in the world and look at them from a different point of view. And the point of view I want to do is I want to get to here, because when I get to here with that point of view, I now have the coplanar. In other words, this point here, and this point here all exist on a flat plane. And the flat plane, if you're going to go back to the beginning again, there is a plane that exists. And if I tried to draw it for you right now, it'd be something like this. Imagine a plane that exists out in space, and there's the plane, and this plane is the plane that those two vectors exist in. Well, as I change my coordinate space around, I effectively turn that into a flat plane, and that flat plane is now a different coordinate space than the one I had, but I don't care. And I've actually just turned a 3D coordinate problem into a 2D problem, because these 3 points define a plane, and that plane now actually sits completely differently to the original one, and I can ignore the third dimension. I can now get an XY thing happening that is like this. So that is now this here represents the 3-dimensional object swung around so it's in 2 dimensions. So that's really important. So point number 1 from the class, actually I should go into Paint to do this. Point number 1 from the class that I was trying to communicate with you guys is that, vectors can move, so we can put the ends together. And because we put the ends together, we end up with 3 points. If we didn't put the vectors together, if we had 2 vectors that were independent in 3 space, then 2 vectors in 3 space, which could be going at like weird angles to each other. Like imagine if I did this as 3-dimensional tubes. Imagine there's a vector like that, and I've got another vector over here that's doing something else that's completely different. Well, that point there, and that point there, that point there, and that point there, they're not coplanar. But I can actually move the ends of these to touch each other, as we did here. So point number 1 is we could move them. And then point number 2 is once we've moved them, we've got 3 points. 1, 2, 3. And because we've got 3 points are always coplanar. They define a plane. So now I can swing the axis around like I did a moment ago and end up with a 3D problem being a very simple 2D problem. So now I've got a simple 2D space. I can now use simple maths to solve problems. And it just so happens that even if I don't swing it round, so that's, point number 2 is like the 3D into 2D. But if I don't swing them round, there is some important maths that I'll be able to do. And so another point that we're going to come to later is that, if 1 is that the vectors move, 2 is that I can change coordinate space, and therefore I can turn a 3D problem into a 2D problem because I get them coplanar. 3 is even if I don't do that, if I stay in 3D, then the Pythagoras stuff still works for working out three-dimensional Pythagorean problems, and so I can work out how to normalize something. If I normalize something, I make all of these vectors the same length, and if they're all value 1 unit long, they become what's called the unit vector. So these become 1 unit long, and now when I've normalized them, I have the unit vectors, and now I can start doing some cool maths with it. And the first piece of cool maths I want to do is I want to be able to say, what is this angle here between these two vectors? And so to do that, I draw a straight line down here. And when that straight line goes down there, I get a right angle triangle. The second I get a right angle triangle here, I know that this distance here, not the whole length, you understand, but just here, this distance is now the adjacent, and this is the hypotenuse. And we know from really simple trig that the cosine of this angle is equal to the adjacent over the hypotenuse. Now, what is cosine? Cosine is a way of unlocking between triangles and angles. This is what I referred to as the Babel fish. This is like the translator. And literally, like if you are a super unbelievably large geek, this is the universal translator of the language of angles to sides. If you're not that much of a geek and you're only into hitchhikers, then it's the Babel fish of translators. And if you know nothing about science fiction, it's just a translator. The point is, it gives us a link between the world of angles and the worlds of sides of right angle triangles. Now, you might say, well, why did I bother doing a straight line down here and cutting into here? Well, the cosine translator only works on right angle triangles. If we didn't have a right angle triangle, if I'd done a line down here to there, I don't have a right angle triangle there anymore. You know, this looks like maybe it's a right angle, but I wouldn't know for sure. Could be, 83 degrees, not 90 degrees. The point is, the second I no longer have a right angle triangle, I can't use the translator. If I can't use the translator, I can't do a whole lot of cool maths like this, and I'm in all sorts of trouble. Okay, so that led me to doing this. The cosine here is a dot product because we discovered that two things happen. The dot product of the two vectors A and B is the same as the cosine of A, which is the adjacent down here over the hypotenuse. So that gave us this marvelous stellar fact that the dot product, and this is just unbelievably cool maths, the dot product of these two vectors A and B equals adjacent over hypotenuse, which is also, oh, by the way, cos of that angle. But we'd normalized it, remember? We'd reduced hypotenuse down to being equal to 1, just the literally value 1, a unit length. And so we went, oh, well, if that's the case, then the dot product of these two vectors, A and B, is actually equal to the adjacent. Wow, there's the adjacent. There's the adjacent right there. It's not equal to the B vector, because the B vector is longer than that, right? But it's equal definitely to part of the B, which is the adjacent. And that was very, very significant. That let us solve the problem, if you remember, of the normals coming in on bouncing up. Because remember we said, okay, well, if I want to have light bouncing off, I have a normal coming out from there, which is always at 90 degrees. I have a light vector, which is defined in computer graphics to point that way. So I reversed it to point it this way, and I now needed to lift it up by two of those lengths there. Now, my good friend Zap would say, I shouldn't have called this the adjacent, I should call it something like Fred. And imagine this length here, this thing here, is called Fred, just for argument's sake. We know that distance there is Fred, and that's Fred, so you lift this up 2 Freds. Well, how do I work out what a Fred is? Holy dooly, a Fred, or an adjacent, is equal to the dot product of the 2 vectors. So I reverse the normal, and I have 2 dot products, and I'm there. I've got my correct vector bouncing off the surface. Okay, so that sounds pretty simple, but what I did is I said, oh, okay, well, let me just get a clean one here. I did it the other way around. In the class, what I did is I started with the idea that if I had a vector in 3 space, imagine this is a 3-dimensional world, the backdrop here. Okay, imagine in this 3-dimensional world I have a vector. I started off by saying, well, we can consider a point to be x, y, and z. So let's say that point is, I don't know, here, for argument's sake. And it's somewhere out in x, somewhere out in z, and you know, vice versa. So it's this point out here. Okay, so there it is there. Now what I think I probably didn't say clearly enough is why I can write a vector as x, y, and z. Why can I write a vector as x, y, and z? Well, the more observant of you would remember that I said I could move a vector. So if I could move a vector to here, being this is the same vector, right? So call this vector A. I'm just going to move it over to here. A vector is defined by 2 points. And so if I take a point, which is my little x, y, and z, and I subtract another point from it, which is the origin, which is 0, 0, 0, what do I end up with? X, y, and z, and that's the vector. So 2 points minus 2 points gives you a vector. The vector only needs one number because it assumes that the other end is at 0. Does that make sense? So if I wanted to define any vector, this vector out here, for example, I move it over so that its end is at the origin. Any 2 points equal a vector if I subtract one from the other. So I get x, y, z. I minus 0, 0, 0 from, which of course is minusing nothing from it, so nothing changes. And I get a vector x, y, and z. Well, that seems pretty cool. So now I have this x, y vector. So let's draw one. Let's draw on 1, 1, 1. What does that vector look like? Well, let's think about it for a second. It's pretty obvious, but I'm going to come out 1 unit here, I'm going to come out 1 unit there, and I'm going to come out 1 unit there. So I'm going to go out to here 1 unit, out to here 1 unit, and up 1 unit because of this. And there is my 1 vector. So assuming that that is 1, and that is 1, and that is 1. And I said at the start of the class that you always tended to have coordinates, Cartesian coordinates, with scales that go positive and negative, and also tend to be linear. These don't tend to be logarithmic or anything. There's my vector. Now, is the length of that vector 1? Well, no, it isn't, because if it fell down right now, imagine it fell down, it would fall down, it would come out further than this length, because it's a long pointy thing, right? It's up in the air. So the 1, 1, 1 vector doesn't give me a length of 1, but it certainly is easy to draw it. Okay, so what can I do with vectors? Well, I was also saying that if you had a vector that came along here, and you had another vector that came up here, that you could, let me just change colours for a second. You could add them together and you'd get another vector that came to here. And I was saying that that was A and that was B, and that gave me C. And I said it didn't really matter whether I swapped the order around, particularly. I could, let me get another colour, and go the other way, and say, well, let's say you'd drawn it the other way. So I want to do B first, right? B comes up here. So that's now B, and I want to add A, and then A goes across here. And I still end up at C. So I knew that, let's go back to white. I knew that A plus B equaled C, but also B plus A equaled C. So that's good. Okay. So I did a bit of this maths, and then I decided, well, wouldn't it be good if I could actually just show you the real maths of how this worked, rather than showing you sort of, vague maths. So we looked at real vectors. So I did 1, 2, and 3, and say 4, 5, and 6. And along the way, I noted that you couldn't do 1, 2, 3 with 4, 5, 6. That would be a column versus a row. You can't do that. And we couldn't do things like 1, 2, 3 plus 4, 5. You couldn't do a 3D plus a 2D. That wouldn't work. And there are a bunch of things you can't do. One of the important ones you can't do, by the way, is you can't say that 1, 2, 3 minus 4, 5, 6, that isn't equal to 4, 5, 6 minus 1, 2, 3. That is not the same. But that's okay. So let's go back and let me just undo that. So I said, all right, how do I do this maths that we've been talking about? 1, 2, 3 plus 4, 5, and 6. And this is a concept from next week or a coming week, but just obviously these are like 1 unit in X, but you think about them as being t-shirts. That's right, t-shirts. So imagine I had some t-shirts. This is going to make life really simple, trust me, though it looks like I'm stark raving mad. Okay, I am an XL. I'm happy to admit it. I used to be bigger, but I've been pretty healthy lately, but I'm an XL. Other people are Ls, John's probably an M. Imagine these represented, not X, Y, and Z, but sizes of t-shirts. We have one, in storeroom 1, we have 1 medium, 2 large, and 3 XLs. And in the second storeroom, we have 4 mediums, 5 large, and 6 XLs. So if I add them together and say I can combine the storerooms, how many medium shirts do I have? I have 5 between the two storerooms. How many large do I have? I have, it's the worst 5 ever, sorry. I have, 7 larges. And how many XLs do I have? You guessed it, 9. So there you go. Now, it helps a lot that we wrote these as vectors, not for this exercise of t-shirts, but when we start getting into doing vector maths. But that's all. Like, it's a column, and each column number, this thing here, represents something in its axis. So if this is now the x-axis, and this is the y-axis, and this is z's, and we think of these as representing units in each of these axes, obviously you're only going to add the x's with the x's, the y's with the y's, and the z's with the z's. It's like a child's game, really. So that's how vector addition and stuff works. And a lot of the other maths works that way as well, except for this marvelous thing that we... let me just give you a clean one of these. Here we go. The dot product. Okay, how does the dot product work? Dot product. Because we don't want the dot product. It's kind of useful. So I'm going to do the dot product of these numbers. Well, this dot product is being done without any of that normalizing stuff we spoke about before. I'm going to do 1, 4 plus 2, 5 plus 3, 6. Now, of course, this no longer works on the t-shirt analogy, which is why I didn't use it last week. But it is what a dot product is. So this becomes 4, this becomes 10, and this becomes 3 6s are 18. Which becomes 14 plus 18, which becomes, you guessed it, 32. Okay, now, this was an important point. A dot product did not return me a vector. A dot product gave me back a number. We call it a scalar number, but just let's call it a number. And that number, we love that number, that's equal to the cos of the angle. If, not in this case, normally yes, but today no, because these weren't normalized. See, because these weren't normalized, we can't say it's the cos. If this had been normalized, we could use the cos. Okay, so how do I normalize a number? How do I normalize a vector? How do I make the length of this vector that's sitting in 3 space how do I make that length here be 1? And we discovered that what we do is we divide it so it's actually equal to the vector by the length of the vector. And so you get the vector and you divide it by the length of the vector. And you can use for the length of the vector Pythagoras, which we did, of course, last week. So let's say I've got x squared plus y squared equals z squared. Then Pythagoras will say that if I give you, x and y, which is, say, the number 4 and the number 3, that you will go 3 squared plus 4 squared equals 5 squared, because you know that 9 plus 16 equals 25, and so 25 equals 5. So Pythagoras, we know z, being that number there, that distance there, is equal to 5. So in the vector that I wanted to normalize in the class, I did that, and I normalized it down. Now, the reason that I don't normally do the math, this stuff, with normalized vectors is that these numbers tend to turn out to be numbers like 0.7.717 or something. They become like really, quite funny numbers. Not funny numbers, they become like more complicated to do in your head numbers. If I normalize a vector, I could end up with a vector that, reads like 0.13, 0.707, 0.962. And so therefore doing the maths of those vectors when normalized is a little more difficult. But that's what you have to do. You have to normalize your vectors for it to work. So what has that left us with? We know how to do... Get out of here for a second. So these are the class notes that I did back then. Remember I did the A and B vectors, and I wanted this cos product. I worked out the adjacent, and oh, by the way, that's the dot product. I worked out that adjacent over hypotenuse equaled this thing, and the only other thing to say is this thing about the cos 0, or cos of the angle, I should say. So not cos 0, cos of the angle. And I went on to explain that even though this magical tool of cos, not in Paint. Let me go into magical tool of Paint. There we go. Okay, so this magical thing here, this thing that this universal translator, this Babel fish, this marvelous thing, is at our disposal. That we could just pull up a normal calculator that you would have had at school, and we could have typed in some numbers, and we could have hit the inverse cos, and that. Like basically, for those of you who don't know, you have cos goes one way and you have sort of what's called inverse cos going the other way. And that basically just lets you go between angles and sides and angles. But whether it's cos or inverse cos, just a calculator or a large book. When my father was at school, they had literally like piles and piles of these things written out in an actual book, and you'd actually just look them up. Whatever it is, whether it's a calculator or a book, we could use this universal translator to go from this formula to the actual angle. And it might tell me that the actual angle is something of significance. But we often don't need to do that in a computer. In a computer, we often don't need to do that. In a computer, what will happen is, once we've worked out that we have some number, let's call this number. We have a number that is equal to the cosine of this angle, yeah? Once we've worked out this number, we just don't bother taking it to the next step of sending it through the translator to get the actual angle. We just store in the computer the cosine of the angle. And the reason for that is tons of computer graphics, tons of it, actually wants the cosine of the angle. The computer itself finds it really useful, as we saw in our examples the other day when we were doing the iPhone, to know the cosine of this angle. It's like if I translated it back to angle, the first thing the computer's going to do is just do it back to cosine again. And it's just, it's dull, it's boring. It's not that it's mathematically complicated, it's just dull to bother translating it and then translate it back again. Why don't you just store it in cos format? Now, if somebody doesn't want cos, if somebody sort of comes along one day and says, I know that you think that you're smart in storing cos of this angle, but quite frankly, I wanted the sine of it. Only then would we go, oh, okay, well, then we'll run it through our translator and get the actual angle and then give you the sine of the angle. but as nearly all of the time we want just the cosine of the angle, that's what we store. Well, I hope that's cleared stuff up for you. I hope that's made things a little simple. If you found this tutorial useful, let me know, because this is a different thing we've never tried before, to have a tutorial about a class, a sort of a slower thing that just goes over some of the points and explains them from a different point of view. Hopefully by me explaining it in a different order and in a different way, it may have eliminated it a little more. I hope this is making sense. I'm desperately keen to make this make sense. This is a marvelous thing. I guess the biggest criticism I took out of last week's comments in the forum was that for a few of you said, look, why did I even care about vectors? And it's so hard for me to even get to a place in my life where I could imagine that you wouldn't love vectors. But vectors are everything because they give us everything to do with computer graphics. They're so fundamental to everything from, working out optical flow to working out shading on 3D objects, that it is at the core of what we do. And so being able to understand vectors is just really, really important. Well, that's it. Thank you so much for our first ever FX PhD tutorial.